Okay, hi everyone. Welcome to class. Today we're going to be discussing the integral test, and that's 11.3, chapter 11.3 from the Stewart textbook. So let me just give a little introduction into what we're going to be talking about. So this is session 11.3, the integral test. Okay, so remember we already started our study of series. So we're going to talk about the integral test. So let me just give a brief introduction, okay? Okay, so just pretty much this is like the motivation of what we're trying to do, or why we need to, actually, let me call it just motivation. So, okay, why we need to study this integral test. Okay, so let me say in most cases, okay, when you're dealing with series, you have cases where it's pretty tough, it's difficult to find an exact sum of the series. Okay, so of course remember that if we have a series, say I from 1 to n of let me just say a particular n, let me call it asterisk. Okay, this is in terms of n, asterisk of n, so to speak. Okay, so sometimes it is tough to find an exact sum of the series like this. So what do? Then we can just, forget about the sum and then just discuss convergence or divergence of that particular series. Okay, so there are times where it's tough to actually find an exact sum of the series. Then we can only discuss convergence or divergence. Okay, so let me write that in words. So in most cases, it is difficult to find the exact sum of a series, or even a formula for its partial sums. Okay, even a formula for its partial sums. Okay, so what do? Now we then explore the integral test. Okay, of course, the integral test is just one of the tests that can be used Okay, we then explore the integral test. The integral test is one of those tests that we can actually use to enable us determine whether a series converges or not, or diverges. Okay, without explicitly finding the sum. Now, keep in mind that we have different series tests, okay? So the integral test is one of those tests. So again, there are situations where you are given a series, you cannot really find its sum because it's pretty tough to do that. So what do you have to do? You just have to rely on your series test. Then you can either talk about convergence of that series or divergence, okay? So let's then talk about the integral test itself. Okay, the integral test. Okay, so suppose we have a continuous function. Okay, suppose f is a continuous, positive, and decreasing function on the interval 1 comma infinity. Okay, close that 1. All right. And let the nth term. Okay, so let me write it down. And let's suppose, and let this nth term be given by f of n. Okay. Then the series. So this is just a statement of the integral test. Okay, this is a statement of the integral test. Then the series, this guy to infinity, infinite series. This guy is convergent if and only if the improper integral, remember improper integral, right? We learned that from 7.8. Okay, so integral from 1 to infinity, f of x dx is convergent. Now, in other words, now let's write this in clearer terms, okay? So because a lot of all this can be confusing, but let's write it in clearer terms. Now, in clearer terms, in other words, number 1, if this improper integral, this guy, if it is convergent, then what happens? Then the series, of an, this guy, n from 1 to infinity of an, is convergent. Okay, I'm going to explain more in a little bit, in a little minutes. Okay, so if we have this improper integral, if this guy is divergent, what happens? Then this series is divergent. Okay, so now as far as the integral test is concerned, there are key things we need to pay attention to. All right, so there are some key things we really need to pay attention to. So let me do it right. Now, the first thing is that the given function, the function has to be continuous. Okay, these are like the hypotheses. All right, so it has to be continuous. Second hypothesis, it has to be positive. And the third hypothesis is that it has to be decreasing. Okay, now when these 3 conditions are satisfied, then you're good to now investigate the improper integral. Now that means I have to convert my series to an integral. All right, so we see that a lot when we do Riemann sums, right? When you do Riemann sums, you see that a lot, that you can rewrite the sum as an integral, and you can rewrite integral in terms of sum. Okay, so these are the 3 hypotheses of integral test. The first hypothesis is that the function has to be continuous. The second hypothesis is that the function has to be positive. The third hypothesis is that the function has to be decreasing. Okay, if one of these 3 conditions or hypotheses, if it fails, then you cannot use the integral test. Now we're discussing different kind of series tests we can use. It's more like there's a condition. Once it satisfies condition X, then you can use this test. If you need to use the integral test, the given function has to fulfill these 3 hypotheses. The first one is that it has to be continuous, it has to be positive, number 2, and number 3, it has to be a decreasing function. Okay, so let's move on. Now, we need to also just take notes. Okay, so let me just, so you want to take notes. It is not necessary to start the series or the integral at 1. Okay, Now, what does this mean? Remember that we have we always have this guy from 1 to infinity, right? Of an. But it's not always compulsory to start this guy from 1. There are cases where we can start this guy from c. Okay, where c is a constant. Okay, let me put it here. C is a constant. It can be bigger than 1, it can be bigger than 0. It depends. Okay. So an example, just to write more on that. So the integral, this guy, this is an improper integral. I messed up on that. This is c here, this is infinity here. F of x dx. Okay, this series will give us information, about, okay, this improper integral will give us information about the series. So what series in this case? N goes from where, guys? This has to be a C. Okay, infinity, then an. So it even gets a lot interesting when pretty much when we're trying to solve example. Okay, so it's going to be easy to go by in that situation. All right, so the first example, so we're trying to answer the question is, let's start from a very basic example. Is the series n goes from 1 to infinity, 1 over n squared plus 1, is it convergent or divergent? Okay, so we're trying to all right, so we're trying to answer the question, is it does it converge or does it diverge? Okay, let's see. So solution. Now, how do we go about this? The first thing you need to do is, remember, you're given this guy, n equals 1 to infinity, right? N goes from 1 to infinity, I mean 1 over n squared plus 1. Remember that this guy itself is my an, right? An is just 1 over n squared plus 1. But can we back up a little bit, back to our statement of the integral test? Okay, in the statement of integral test, we said that let this guy be true, right? Let an equals f of n. All right, so that means, what do I do in this case? Okay, watch me. So I'm just going to say, consider the function f of x equals 1 over x squared plus 1. Okay, so what happens? Okay, so what happens? So consider this function on 1 comma infinity. Now, how do I know this interval? Good question, guys. Remember that your n is running from 1 to infinity. So that's why you have a 1 here to infinity. Now, if this guy is n running from 2 to infinity, that means this interval has to be a 2 to infinity. Okay, make sense? Nice. Now, what are the 3 hypotheses? Okay, remember, hypothesis. What are the hypotheses? My function must be continuous, right? The function must be positive, and the function has to be decreasing. So I must check to ensure that my function f of x equals 1 divided by x squared plus 2 is continuous, positive, and decreasing. Okay, let's see. So number 1. So let's say we're trying to answer the question, is f continuous? Okay, so now do you remember calculus 1? where you actually studied continuity. Now take a look at this, your f of x. F of x is 1 over s squared plus 1. What is this on the bottom? This is a polynomial, right? So do you remember that all polynomials are continuous? Okay. You remember that all polynomials are continuous? Good. Now that's what you have on the bottom. So let's start by saying that f of x is continuous since s squared plus 1 is continuous. Why? All polynomials are continuous on set of reals. Okay. All right. Makes sense. We know all polynomials are continuous, and then we have to be able to fix it. All right. Can we proceed? I guess yes. Remember, we have to make sure the three conditions are satisfied. They have to be satisfied. If it fails, then it cannot work. Okay. So what's the next thing I'm going to do? Okay, so next thing I'm going to do is now, but take a look. The only statement we have here is just for the bottom. What about the top? Okay, so as long as we have 1 divided by that guy, it's still going to be continuous. Okay, but I have to add a caveat that s squared plus 1 is not equal to 0 on that interval. Okay, now what happens, what happens if it's what happens if this guy equals 0? There's going to be a problem, right? If s squared plus 1 equals 0, that means that you have 1 over 0, and this is a problem. So, and in this case, it's not continuous. Okay. All right, so let's move on. So what is the second hypothesis? We're trying to answer the question, is f positive? Okay. Okay, so let me write a little bit more here. Continuous on the set of real numbers since our discussion. Okay, all polynomials are continuous, yes. So let me write it like this. Our setting is R. Our setting in this course is R. R means the set of all real numbers. So let me write this clearly. Setting is this in this class is R. Okay. So let's move on. Is F positive? Okay, so what's the conclusion here? Let me write it here. The answer here is yes, continuous. Okay. Now, is it positive? What do we do? F of x is actually positive. Let me remind you what the f of x is. 1 over s squared plus 1. Now, what kind of number will this guy produce? Remember that the interval is 1 comma infinity. Pick any number. Think about the number line, right? This is 1. You're picking any number here. Plug it here. It would always be positive. Okay? So since s squared plus 1 is greater than 0 on 1 comma infinity. Okay, it will always be positive. Okay. And also 1 divided by x squared plus 1 is still going to be positive on this guy. So what's going to be our conclusion, guys? We'll say again, yes, f is positive. Okay, what's the third hypothesis? The third hypothesis is we're trying to check, is f decreasing? Can I remind you of f again? 1 divided by s squared plus 1. Okay. Now, what do you do here? I encourage like a calculus thing here. I encourage you to do like a calculus thing here. And let me just let you know that's probably I should write the definition here. Note: a function f is decreasing if f prime of x is less than 0 on a given interval. Okay, on a given interval. So let's see what happens. Now, what do I need to do? That means I need to take derivative, right? Because this is the first derivative. So let's just do that. If you take the first derivative of this guy, you get a negative 2x divided by s squared plus 1 all square. That's quotient rule, guys, quotient rule. Now, what kind of number is this guy going to produce? It's going to produce a number less than 0, but you have to specify the interval, right? On 1 comma infinity. If you pick any number here, if you plug in a 1, plug in a 2, plug in a 3, the output is always going to be negative. So what's going to be our conclusion? So f is decreasing on what interval? On 1 comma infinity. Okay, so our 3 hypothesis is satisfied. Number 1, continuous. Number 2, positive. Number 3, decreasing. So now we are free to use the integral test. If any of these things fails, then we cannot use the integral test. We cannot even talk about it. Okay, so thus we can use the integral test. Now, at this level, what happens? You're going to formulate your improper integral from 1 to infinity. Remember, the question was n from 1 to infinity, 1 over n squared plus 1. So this is your 1 to infinity. You got 1 to infinity. Write this guy in terms of x. So you have 1 over s squared plus 1 dx. You remember we learned improper integral, so we have to bring it on. Okay. So you write this guy in terms of the limits. Limit as you can use k. K goes to 1. K goes to infinity, my bad. Okay, so you have a 1 to k, 1 over x squared plus 1 dx. Okay, so but if you integrate this guy, what is this guy? It's just the arctan, right? Do you remember that? That's just arctan. So limit as k goes to infinity. This is going to be the tan inverse of x from 1 to k. Okay, so if you don't know how this is equal to the tan inverse, you might want to look up the old videos where we did trigonometric substitution. Okay, I can just rewrite this guy as the limit as k goes large. This is going to be like the tan inverse of k, okay, minus the tan inverse of 1. Remember how we do the top minus the bottom. Okay, so this is the limit as k goes large. All right, so this is going to be a tan inverse of k. What is the tan inverse of 1? Okay, that's pi over 4. That's 45, right? And that's exactly pi over 4. Now you want to find these limits. Okay, so let's see who remembers how to compute limits. What is the limit as limit of tan inverse of k as k goes to infinity? Okay, remember, if you graph the tan function, you have asymptote at pi over 2. So that means this guy is just pi over 2 minus pi over 4. And this is exactly what, guys? Pi over 4. Now, when you compute, remember, what is the definition of convergent sequence? Now, let's go back to sequences in 11.1. When we dealt with sequence, we said the limits must be finite, right? So intuitively, we can transfer that kind of definition here. This limit is finite. Then what is going to be our conclusion? So we just say, therefore, this guy, as n goes from 1 to infinity, of 1 over x squared plus 1 is convergent. Okay. Now, but there's going to be a warning, guys. Let me just chip in this warning. Remember, what does the integral test helps us to do? Does it help us to find the sum? No, guys. It only helps to determine if a series is convergent or divergent. So let me just give that warning right now. Note, this guy, this sum, or what we call the series, is not equal to pi over 4. No. Okay. The integral test let me capitalize this, only tells us if a series is convergent or divergent. Okay, this is an important point. Okay, the integral test does not give us the value of the sum. Okay, integral test does not give us the value of the sum. It doesn't. Now let's look at another example. Okay, so example. Okay, so in this example, let's see a different function. In this case, you have this guy, 2 to infinity, ln of n divided by n squared. Now, remember that what do we need to check? Solution. If I need to use the integral test, what are going to be my hypotheses? Okay, so can we just remind ourselves, hypothesis is that it got to be continuous, got to be positive, and it has to be decreasing. Okay. If it satisfies this condition, and that condition, then you can apply the integral test. If it fails, then you have to think about something different. Okay. So let me just say that we have to study f of x equals ln of x divided by s squared. Okay, so I can just say consider or study. Okay. Now, on what interval, guys? Can you help me out? That's just going to be what? 2 comma infinity, because right here you have a 2. Okay, so what do I do? Let's see if we can answer those questions also. Number 1, is f continuous? Is f continuous? And let's see, what is the answer? The answer is yes. Now, how? You don't just go ahead and answer yes without giving the reason, okay? So yes, why? Since my s squared is greater than 0, and s squared is a polynomial, okay? And ln of x is greater than 0, on those interval. Oh, okay. The first question I answered here from my notes is f positive? Okay. Now, again, guys, anyone can come first. You can check if the function is decreasing first. You can check if it is positive first. It depends. So in this case, I decided to, my note, I did it differently. So it's f continuous. Let's see. Take the, if you have this kind of rational functions, you take the numerator, you discuss it. You take the denominator, you discuss it. It happens that in the denominator here, our s squared is greater than 0, right? And our ln of x is greater than 0 on this interval. Okay, so it's not as if we're creating a different interval of our own. We're working with the interval given from the series. Okay, so number 2 question we're trying to answer. Now let's answer a question of continuity. Is f continuous? What do you think? Is it continuous? Okay, I think I already gave her the hint the other time, so it's yes. Now why? Okay, let's remind ourselves f of x is just ln of x over x squared, right? Why is it continuous? Do you have a reason for me? All right, so now let's see, what's the numerator? Ln of x. This guy on the bottom is always continuous. Why? Because it's a polynomial. So that means my emphasis has to be on the top. If f of x equals ln of x divided by s squared, if it must be continuous, then both the top and the bottom has to be continuous, okay? So how do I discuss this guy? Okay, so ln of x divided by s squared does not have points of discontinuity in this interval. Okay, it's a way to think about it. Now in this way now, I combine both the top and the bottom together. Now, how do I know it doesn't have a point of discontinuity? Because this is 2 to infinity, right? Not 0. If we're going from 0 to infinity, there's a problem, okay? Why? Because on the bottom, you have a 0. ln of 0 is 0. You have a 0 divided by 0. That's already a problem, okay? So, and also, I can say that my ln of x is actually defined. This guy is defined everywhere on 0, infinity. Remember that the ln function can never take a negative sign, okay? Something like ln of -1, ln of -100, that is not possible, okay? And my s squared, of course, is different from 0, still in that same interval, okay? Okay, so ln of x is defined everywhere. And this guy is not equal to 0. Okay, of course, if this guy, if s squared is not equal to 0, that means x cannot be 0, okay? Which means that x cannot be 0. All right, so how do we conclude this? We already said ln of x divided by s squared doesn't have a point of discontinuity in 2, infinity. ln of x is defined everywhere here, and this guy is not equal to 0. So f of x is continuous on 2, infinity. Okay. Now, what about the third hypothesis? Can we just answer the third hypothesis? What's that? Is f decreasing? So what do I need to do? I need to just do my derivative test, right? What is f of x? Ln of x over x squared. what do? I do quotient rule. F prime of x. If you do quotient rule here, differentiate the bottom. Okay, and if you do the quotient rule of this guy, you have a 2x here. Okay, this is going to be, all right. So here I'm going to have, keep the bottom constant, differentiate the top, you have 1 over x. All right, so keep the top constant, differentiate the bottom, you have a 2x here, divided by the square of this guy. So what do I have? I have a x minus 2x ln of x divided by x to the fourth. And what is my f prime of x? My f prime of x is just going to be x 1 minus 2 ln of x divided by x to the 4. Okay, can anything cancel? Sure. This guy can reduce this power. So you have a 1 minus 2 ln of x divided by s cubed. Now, but remember that if f is decreasing, then I expect that this quantity has to be less than 0. So what do I need to do? So that's where the work lies. Okay, so take a look at how we do this. Look at the bottom. S cubed is in the given interval. What is our interval? Remember, it's 2, infinity, right? In that interval, s cubed is greater than 0. So what do we need to do? I only need to focus on the top. So study 1 minus 2 ln of x. Okay, the denominator is always going to be positive, but I need that guy to be I need the whole of everything to be negative. Okay, so to study this guy, see what we do. If this guy is less than 0, for what value of x will this guy be less than 0? So I can do something like this. Let us see. For what value of x will this guy be less than 0? That's what I'm trying to solve. Okay. So divide through by negative 2, the sign flips. And then if s is greater than 1/2. What do you think, guys? I need a value of x. So that means I can do e to the ln of x, right? Bigger than e to the 1/2. That means x has to be bigger than square root of e. Okay. So what do we conclude? So f prime of x is less than 0 for x greater than square root of e. Now there's something to check, okay? What kind of number is e? Remember, e is like 2 point something, right? The square root of e is approximately 1.648. Now in the 1.648, right? Good. Now, this kind of number, okay, so but now it says x is greater than this number, okay? S is greater than square root of e. Now, if I even want to do like a sharp approximation, I can just approximate this guy to 2. Okay, so now since the square root of e is less than 2, okay, how do we conclude? F prime of x is less than 0 on 2, infinity. Now, I'm going to explain, guys. Don't be confused. Now, we started here to see if f decreasing. We did the first derivative test. We ended up with 1 minus 2 ln of x divided by s cubed. Now, but how do I go about this sort of thing? I need to determine if it is less than 0. Of course, I cannot just come here and just claim less than 0. The next question becomes how? You have to show it, okay? So to show that, I have to discuss this rational function, discuss the bottom, and discuss the top. So I pick the bottom. within the given interval 2, infinity, this guy on the bottom is always positive within this interval. So what am I left to do? That means the only thing that can determine if the first derivative is negative or not is the numerator. So then I pick that guy, I study it. If you want to study that guy, that means the question you're trying to answer there is that for what values of x value, in this case now, because it just has to be, at least it's starting from a point. So we can just claim that for what value of x will that guy be less than 0, okay? So this is a 1 minus 2 ln of x less than 0. Take this guy to the other side, you have this guy. This divide through by -2, the sign is going to flip. And then you have this guy. So just now at this point, you need the value of x. What do? Take e of both sides. Take the exponential of both sides. So that means your x is bigger than this guy. So that means your derivative, first derivative is negative. For what value? This value of x. Now, why do I need this part? Let me put it in red. Why do I need to even say something about this part? Okay, so I need to do that because I need to look at the interval I am considering. Okay, so I need something with which, now square root of e is less than 2, right? So, but x is greater than this guy. So I can pick x to be 2.5. I can pick x to be 5.0. I can pick x to be 20. Okay, so it doesn't really matter. So, but here, that means that f prime of x is less than 0 for this guy. So every other thing becomes easy because all the 3 hypotheses are satisfied. Okay, so let me say all hypotheses of the integral test are satisfied. So now, okay, so I'm gonna put so now. We have to compute the improper integral from 2 to infinity, ln of x divided by s squared dx. Now, at this point, you now have to rely on your knowledge of integration. Okay, so how do we integrate something like this? Any idea? Okay, and that's integration by parts. Okay, interesting, right? Okay, ln of x divided by s squared dx. This is going to be x to the -2 ln of x dx, right? I'm just rewriting it. So what can I do? Remember how we do integration by part? Let u equals ln of x. What is du? Du is just 1 over x dx. Okay, what about dv? dv is going to be x to the -2 dx. How do you find v? Integrate. So what is going to be my v? -1 over x. Okay, so we know u and v, but remember that the formula is where u dv is just uv minus integral v du. Okay, so that means this guy is x to the -2. This is integration by part formula. Okay. ln of x dx. So this guy is really going to be ln of x because that's u. What is your v? Minus integral of, you got a -1 over x, 1 over x dx. So this is going to be negative ln of x divided by x plus integral of 1 over x squared dx. Okay, so we're still in the game, we're still solving. This guy becomes negative ln of x divided by x. You have a minus 1 over x plus c. Okay, so that's the indefinite integral part from this guy. So now can we plug in the bounds? Okay, definitely. Can we plug in the bounds? Definitely. Okay, remember that at this level now, I will now write in terms of the limit definition. Okay, so pretty much I could have also done that from the beginning here. Okay, I could have also just done that here. Ln of s over s squared dx. Okay. So can we go ahead? So limit as k goes large, negative ln of x over x minus 1 over x. Then you plug in your 2 and your k. Okay, so let me do that. Limit as k goes large, negative ln of k divided by k minus 1 over k. That's the top, right? Minus, what about the bottom? Negative ln of 2 over 2 minus 1 over 2. If I do the simplification of this guy, k goes large. Okay, what do I get? This is like negative ln of k divided by k minus 1 over k. Okay, so this is plus ln of 2 over 2 plus 1/2. Interesting. Who remembers how to find limits? Now, if you find the limit of this guy, okay, so let me split it. This is limit as k goes large. I don't want to get anybody confused. Minus limit as k goes large of 1 over k plus the whole of this guy is a constant. So limit, and you know the limit of a constant is just a constant. So this guy will go to 0. Okay, so again, I don't want to get anybody confused. So let me just write it here. Now, but right here, there's a problem, right? This guy, if you plug in infinity, you have like something like negative infinity over infinity, right? So, but you can do the L'Hopital's rule. So this guy is going to be, of course, remember you have infinity over infinity, right? So you use so what am I going to do? Differentiate the top and the bottom. So that means you do limit as k goes large, negative 1 over x divided by 1, okay? And this is limit as k goes large, negative 1 over k, not x. Because our discussion at this point is k. Now, what's this limit? 0. Perfect. Perfect. Okay, so this guy is 0. Okay, so what's our conclusion? That we're going to have ln of 2 over 2 plus 1/2. Okay, so how do we conclude? So I can just also write this uniquely, okay? So since the improper integral converges, by the integral test, the improper integral is not converging by the integral test, right? Remember, you know how improper integral converges. So we're just saying now by the integral test. So maybe I should put that there so that nobody gets confused. So now, by the integral test, okay, just to ensure clarity. by the integral test. What is the series we're discussing? We had the sum as n goes from 2 to infinity. ln of n divided by n squared converges. It does converge. It does converge. Amazing. Okay. It is explicitly amazing. Okay. So let's see if we can just do one more example. And then we would go from there. So let me see a nice example that we can talk about. Okay. Okay, so before we do that, perhaps I should just discuss the P series. Okay, so we have something we call the P series. The P series. Okay, so this is also a very important one. So a series such that we got 1 plus 1 over 4, 1 over 9 plus continues on and on, which I can still rewrite as 1 plus 1 over 2 squared, so 1 over 3 squared, continue on and on, infinite. Okay, this guy can be written as this. A series such that this is true is called a P series. Okay. So in general, a P series follows the following form. And that is n goes from 1 to infinity, 1 over n to the power of p, and then you have a 1. Just plug in n. This is like 1 to the power of p. Plug in your 2. You have 1 over 2 to the power of p, 1 over 3 to the power of p, on and on, guys. Now let me state a theorem, a very useful theorem, guys, that centers on the P series. Okay, so the P series okay, so this is n to the power of p. This p is a power. It's the index, okay? It's convergence if p is greater than 1 and divergent otherwise. Okay, so a P series converges if the index p is greater than 1 and it diverges otherwise. Okay. Now, note when p equals 1, this guy, n from 1 to infinity of 1 over n, is called a harmonic series. Let me write it clearly. It's called a harmonic series. Okay, and how would that look like? This is like 1 plus 1 over 2, 1 over 3, on and on. This guy is just 1 to infinity, 1 over n. Okay, so now can we use this theorem? This theorem says that a P series converges when P is greater than 1. But in this case now, what's my P? My P is 1. So we need to say that harmonic series diverges. Okay, so I need to state that the harmonic series does not converge. So in bracket, what do we say? Diverges. Okay. I hope that makes sense, guys. I hope it makes sense why that is true. Now, let me give you an example. If we have this series 1 over n squared. So what do you need to do here? You don't even need to think about because this is a simple one. You don't have to think about the integral test. So what is P? Solution. P is 2. And by P series test, this guy does what, guys? Converges. Because what does a P series test require us? P has to be greater than 0. P has to be greater than 1, my bad. So, and 2 is greater than 1, obviously. So because 2 is greater than 1, then you're good. Okay? Does that make sense? Okay, so I think this is going to be okay, so let's see if we can do one more. Let's do one more and then we'll stop there. So example, you have the series 1 divided by the cube root of n. How do you treat this guy? Okay, solution. So can I write the guy on the bottom? Yes, I can, right? And let me take off my parentheses. So this is like 1/3. Now, what is the value of P? Okay. If I want to write this guy, this is like a 1 divided by 1 to the power of 1/3 plus 1 divided by 2 to the power of 1/3. And you know, this guy, P is 1/3, right? Then this guy diverges since P equals 1/3 and that guy is less than 1. Diverges by P series test. Or for short, you can call it by P test. P test. Okay, I hope this makes sense, guys. All right, see you in the other session. Bye-bye.